Hi everyone, my name is Shreya and this is my last lab 6 for Physics 2. And so a quick introduction of this lab. So the purpose of this lab was basically to explore the non-induced or the induced non-Coulomb electric field and current that is induced by a falling bar magnet that results in an opposing magnetic force, which essentially slows down the fall of that magnet inside of a conductive tube. And this happens because of Faraday's law. So this is a great demonstration of exactly what Faraday's law shows. So some of the important equations that we have used in this lab is obviously this first one, which tells us how to calculate the magnetic field. Um, and then we also have the magnetic flux calculation equation. This one here is Faraday's law, which is extremely important for this lab. And then obviously Newton's second law, which will help us update velocity and position and determine the next net force for this lab. And then something I didn't list here is the force of gravity, since that's something that obviously applies to any falling object, including this magnet. So our lab experiment, I can give you kind of a brief overview. Essentially, what we did was we took a tube of foil with the following dimensions. We had a tube length of 0.485 meters or 48.5 centimeters. We have a half a centimeter width of this tube, and then an inner radius of 1.5 centimeters, which brings us to a total radius of 2 centimeters on this tube. And we essentially dropped this bar magnet with a magnetic dipole moment of 3.6 through this tube, and we did five trials of this. We timed how long it took for the magnet to fall through the tube. And our average of this was 0.942 seconds. So, in addition to this, I coded a simulation that would allow us to once again come up with like a time that it would take for this magnet to fall through a tube, given the measurements that we took from the lab. And so the first thing we did for this was I started by setting all the correct constraints that I gave in the previous past two slides for the tube geometry, as well as the magnetic dipole moment of the magnet itself. And then after that, I wrote methods to calculate the magnetic field and flux right here. So this one we've used in previous labs, but for the flux, we had to use kind of that equation where you would do basically the B field times the area of like one ring. Um, and we're considering the tube to be a series of many rings. Okay, and then we found the current in each ring and the B field caused due to each ring at one moment of time. So I guess we can think of this as an integration problem, looking at that ring to be like a dr. And so we essentially found like use these to find like the magnetic fields, and then from there we found the magnetic force. Um, and we also found the gravitational force, which is constant throughout. And then the last step of this was obviously calculating the net force, where we add the magnetic force, which points up, and then the gravitational force, which points down, at each time frame. And then we change the velocity, and the instantaneous position of the magnet for time. So when I ran this, you could see the magnet falling through the tube. And we can also see the velocity versus time graph. And as we were expecting, the velocity obviously decreases over time, but then here we see a flat line, which means we've reached a terminal velocity. And that makes sense because we have two opposing forces while the magnet is in the tube. We have the force of gravity, and then we also have the force of the magnetic force due to the current that's induced in the tube, the conductive tube. So with that terminal velocity, that is exactly what slows down our magnet. And the amount of time that my simulation outputted for this magnet to fall through was 0.931 seconds. That was very close to our answer when we did it in real life, which had a difference of 1.12%, which is pretty good. Possible sources of error in this experiment was due to human measurements when it came to tube dimensions, could be reaction time from when we stopped and started our stopwatch, as well as measuring the magnetic dipole moment of the magnet using the phone magnetometer. And then also we didn't consider air friction or resistance in this lab. With our what ifs, we consider the first one. If our resistivity of the conductor was basically zero, that would just mean that our current would be super high, and that force of the magnetic force would counteract the force of gravity more, so the magnetic might not even fall through or be really slow. Second one, if there were holes or slots cut into the tube, the Essentially the induced current would be a lot smaller with like less area to go through, and so the magnet would fall through the tube faster. Thank you so much.